Hello, in this video we'll be talking about facilitated diffusion. So let's not waste any of your time, let's get right to it. Alright, when we're talking facilitated diffusion, again we want to emphasize those passive transport principles. That no energy is used. Okay, no ATP is involved in generating energy so this transaction can happen. And as always, it moves with the concentration gradients or the concentration amounts. If there's a bunch on the outside and very little on the inside, then things are going to move into the cell. If there's a bunch on the inside and not much on the outside, then the same thing. The things will move outside of the cell, all designed to create equilibrium, to balance it out. So passive transport, diffusion, facilitated diffusion are all trying to do the same things, balance out the amounts. If we've got 20 on the outside and 10 on the inside, that's a total of 30. So we're going to try to move things around to where we get 15 on each side. But facilitated diffusion is a little different in the fact that it does use a protein pathway. And again, it's an open pathway. I used, when we talked passive transport a couple of videos ago, I referenced a tunnel into a mountain. Okay, that tunnel is always open. You can think about a bridge over a river. You know, the one that comes to mind is the Truman Lake Bridge going to Warrensburg. That's a pretty long bridge, but anyway, it's always open. Anybody can drive across it. Just moving things from one side of the lake to the other side of the lake. But again, no energy is required, and it moves with the concentration amounts, concentration gradient. Now, when we're talking facilitated diffusion, okay, we want to recognize that the molecules, they don't just get free. It's a struggle to kind of get through. They're a little bit larger maybe now, but again, it's the idea of high to low concentration. We can do channel proteins, okay, when they're just open. We can do ion channels, okay, like the sodium potassium pump would be one of those, where a particular protein is designed to move across sodiums or potassiums. Okay, or maybe it's the ion is just something else, and it's got a particular protein to do that. Okay, maybe it's a carrier protein. Again, no energy. Okay, it's open, but the molecule has to be recognized, or it has to fit. Is a better way of talking about that. But we're going to talk about each of these, but it's the idea of getting things across, okay, and it may be a specific protein for that specific molecule or ion, but facilitated diffusion will make it happen. Okay, now we're talking channel proteins. Had to look around my camera there for a second. Okay, we're thinking about ion channels, okay, which is designed to get ions through. Of course, an ion, if you remember from chapter 2, it's just simply a molecule, not a molecule, an element that has gone through some sort of bond. Okay, it has lost or gained an electron, and therefore now it's not balanced anymore. So it's an ion, it's a positive charge, it's a negative charge. And it's the idea of getting that thing through the membrane. Now, a couple things can come into play here. It can be diffusion situation to where there's a bunch of sodiums on the outside, and they need to be moved. Some of them moved in the inside because there's not many on the inside, or it could be a reference to the charge. Maybe the outside of the cell is a positive charge because there's a bunch of positive ions out there, and on the inside you've got a bunch of molecules that never ever leave the cell, and they're always negative. The negative anions. The large molecules, proteins come to mind, but they're negative. So the inside of the cell is always a negative amount, and it varies from extreme negative to like a negative 70 where your neuron's set at, but it's always a negative amount. So the ions on the outside may be being influenced to move inside because of the charge difference. There's a bunch of negatives on the inside and a bunch of positives on the outside, so the positives will move in. So it's not always just about the particular ion or molecule. It could also be charge driven. That's an electrochemical gradient that we're going to refer to here in a little bit. But it's the idea of what moves across, maybe because of the abundance of that ion, or it could be abundance of a charge on the inside or outside that's causing that. Okay, now we reference carrier proteins, another type that is involved with facilitated diffusion. Okay, we're thinking about getting ions across. Maybe even some sugars, some glucose, and amino acids, perhaps even. But there just got to be a concentration difference across the membrane, and we've talked about that a bunch of times. That just simply means that there's a lot more on one side than there is on the other side. Okay, but the idea with the carrier proteins is they have to recognize what it is, so they got to bind to it. Just to say, okay, yeah, that's something I can move across. And then the idea of saturation, rate of transport would be quicker or slower. And again, the example there is, think about if I've got one door into a room and a bunch of people trying to get in, then it's just single file moving across. But if I open up a second door, okay, a second carrier protein, then that's going to get things through in a much quicker manner. And on our next screen, we're going to see an example of carrier protein. All right, so here's how a carrier protein works. You can see the element there, and it doesn't identify. It doesn't really matter what it is. But the carrier protein, you can see in the first picture, a little bit of attachment, the one on the far left, a recognition of what we've got. But not only that, as it's going through, the protein kind of fits the same shape as the molecule. So again, there's that check as well. And then of course, then it's released into the inside. So it's not just a straight open like the integral path proteins are. A carrier protein is more specific to that molecule with the recognition and the shape. And this is kind of like a key going into a lock, kind of an idea. That's why not every key opens up every lock. If it doesn't fit the pathways or the stuff inside, it just simply won't do the job. But that's the idea of carrier proteins. Well, that's our video over facilitated diffusion. When we come back next time, we're going to be talking about osmosis. So we'll see you then.